And what we're going to start with is names of molecular compounds. So just to recap this particular chapter or chapters, what we have been working on in class and in the laboratory is chapter 4, 5, and 6 of your textbook. Chapter 4 was a very meaty chapter. Chapter 4 had the naming of ionic compounds, which we have been doing in class. It had the Lewis structure of ionic compounds, the Lewis structure of covalent molecules, and VSEPR theory, all of which we did in the laboratory. Chapter 5 had valence bond theory, and no, that's chapter 6. Chapter 5 had molecular shape and bond polarity and molecule polarity. And chapter 6 had valence bond theory, all of which we've been doing in the laboratory. Now, the one thing that chapter 4 had that we have not covered, well, there's actually two things, is naming of molecular compounds and then some mathematics associated with molecular compounds. Now, I am also bringing in something that isn't introduced until chapter 8, which is the naming of acids. I'm going to bring that in today as well. So we're going to finish up naming today. Is the goal. Names to formulas and formulas to names. That is the goal for today. So that you have all of the naming, all of the Lewis structures, all of the VSEPR, all of the valence bond theory, all of the molecular polarity, all the bond polarity, and all the bonding types done by the end of today. We will still have the mathematics associated with molecules, and we will then move on to balancing chemical equations and starting to deal with chemical reactions next week. So let's get into names and formulas of molecular compounds. The first type of molecular compound we are going to talk about is a binary covalent molecule. First of all, let's start with just the term covalent molecule. What does that tell me with respect to the type of elements that are involved? It's two nonmetals or a nonmetal and metalloid. In other words, we're dealing with the right-hand side of the periodic table only. When I talk about covalent molecule, do the bonds arise from an electrostatic attraction between a cation and an anion, or do the bonds arise through the sharing of electrons between two atomic nuclei? They arise through the sharing of electrons. So the right-hand side of that periodic table, when two or more elements combine, they combine by sharing electrons. And because they share electrons, the number of molecules that those nonmetals and metalloids can make is astronomical compared to the number of ionic compounds that can be made. All because of the way their bonds arise, which is through the sharing of electrons. What that means is the same two elements can form more than one type of compound. For example, one that I've already given at one time is CO and CO2. Another one that I've given is H2O and H2O2. The same two elements can form multiple compounds. So we need a process to differentiate because no two compounds can have the exact same name. So we need a method to differentiate what compound we're working with. That method is by using prefixes. We place a prefix in front of the name of the first element. We then place a prefix in front of the name of the second element, where the second element gets the ending IDE, just like it did when we were dealing with the anions. They got the ending IDE. Well, we're still dealing with the ending IDE here. So it is the first thing we need to do is determine what these prefixes are. If you have only one of an element, the prefix is known as mono. Now we only use the prefix mono for the second element in a binary covalent molecule. In other words, we're not going, if there's only one of the first element, we do not call it mono. We only use mono for the second element. Now the rest of the prefixes we use on the first and the second element, depending upon the quantity. So for 2, we use the prefix di. 3 is tri. 4 is tetra. 5 penta. 6 hexa. 7 hepta. 8 octa. 9 nona, and 10 deca. One thing I would like you to note is, for the most part, if I said a triangle, how many sides does a triangle have? 3. That's why the prefix is tri, for 3. If I was talking about a stop sign which has 8 sides, what is the prefix for the stop sign? Octagon. It's an octagon, so it's octa, just like the prefix here. Now, when working with these prefixes, if the prefix ends in A, which the majority of these do, and the element begins with an O, technically with an A too, because you can have arsenic. But so basically we're talking arsenic and oxygen here. If the element begins with an O, then you eliminate the A in the prefix. In other words, we're not going to say pentaoxide. We call it pentoxide. Folks, as far as this last thing, if you goof and put an A next to an O, I'm not going to count you wrong. As long as you got the prefix correct and the element correct. I'm not that nitpicky. So going back, well, if I can get this to work, there we go. CO has one carbon and one oxygen. The prefix for one is mono, but we don't use mono on the first element, only on the second. So that is why CO is carbon monoxide. We are literally saying there's one carbon and one oxygen in this compound. The next one, there's one carbon and two oxygens. Again, we don't use the prefix mono on the first element, but we do use prefix for the second element. So that's carbon dioxide. The name is literally saying there's one carbon and two oxygens. Now, water and peroxide are a little different. I just wanted to use those as examples. Now, I do want to make note of something. The only time you are going to use these prefixes is for the binary covalent molecule. You're not using prefixes in ionic compounds. You're not going to use prefixes on the alkanes, which I'm going to discuss here in a minute. You're not going to use prefixes on the diatomic elements. The only time you are to use prefixes is for the binary covalent molecules. I am saying this because invariably I am going to have somebody that puts prefixes on ionic compounds or puts prefixes where they don't belong. So I'm warning you. The only time you're going to use prefixes are on what type of compound? The binary covalent. Otherwise, forget them. Don't use them, except on binary covalent molecules. So let's look at a couple of examples. Let's name our friendly free radical that we've been dealing with in lab. We have one nitrogen and two oxygens. We are going to literally write the name to say that there is one nitrogen and two oxygens. Now, again, we don't use the prefix for one associated with the first element. So that is nitrogen. Then we use the prefix for two, that is di, and our second element is going to have the ending IDE. So this is dioxide. So that's nitrogen dioxide. In the next one, we have two nitrogen and four oxygen. We're literally going to state that because this is a binary covalent molecule. The prefix for two is di. Then we tell it it's nitrogen. The prefix for four is tetra. So it's tetroxide. Binary covalents are easy because you literally are telling me how many of each element's present. To get to the formulas of binary covalent molecules, all we do is translate the name. Sulfur trioxide. No prefix means what? 1 sulfur. Tri means 3 oxygens. So the formula for sulfur trioxide is SO3. Not to be confused with SO3 2-, which is a polyatomic ion sulfite. The only difference is it charged or is it neutral? The next one is tetra, meaning 4. Phosphorus. Deca. Oxide. Or you could have said decoxide. In this case, it's P4O10. We're literally stating exactly how many of each there are. Questions about binary covalent molecules? It seems easy right now, correct? It doesn't get hard until you mix them all up and have to be able to identify whether you got an ionic compound, a binary covalent compound, an alkane, a diatomic element, an acid, or what do you have? That is one reason in the homework section, the optional homework, there is this huge packets. One of them has 160 questions where you can convert formula to name. The other one has 100 and something questions where you convert name to formula. I did that, and they are all mixed up, just like you're going to see on an exam, because you've got to be able to distinguish between what you're working with. This takes more practice than it seems. Yes, naming binary covalent molecules, if all I got is binary covalent molecules, is easy. But it's not so easy once you mix them all up. Or at least, so I've been told. So practice it. I keep mentioning this word alkane. There are 6 alkanes that you have to know. I meant 6. There are 10 alkanes that you have to know. First of all, what is an alkane? An alkane is a compound of carbon and hydrogen only, that consists of single bonds only. So an example is methane. Methane is a compound of carbon and hydrogen only, and it also consists of only single bonds. Another example would be ethane. Ethane has 2 carbons and 6 hydrogens, but it still consists of carbon and hydrogen only, and consist of nothing but single bonds. So an alkane is a compound of carbon and hydrogen only that consists of single bonds only. The second thing about an alkane is it has the generic formula of C subscript N, H subscript 2N plus 2. I give that information because if you know how many carbons are in the alkane, you can get to the number of hydrogens. Because if there's one carbon, then the hydrogens are 2 times 1 plus 2, or in other words, it is CH4. If there are 3 carbons, then the number of hydrogens is 2 times 3 plus 2, or in other words, it's C3H8. Now let's talk about the name. You're going to have to memorize because you can't deduce. You're going to have to memorize your first 4 alkanes. You have methane, ethane, propane, and butane. And the majority of those 4 alkanes are extremely common. Methane gas is a byproduct of cows farting. Propane is the gas used to heat homes. Butane is the gas that's used in lighter fluid. You just have to know methane, ethane, propane, and butane, or meth-eth-prop-bute. I don't need to know the ane because if it's an alkane, it ends in A and E. All of the alkanes end in A and E. So you got to know meth-eth-prop-bute. Now, once you get past butane, it gets easy. Because we go back to the same prefixes, essentially. 5, a pentagon. Well, 5 is pentane. 6 is a hexagon or hexane. But you got to remember meth-eth-prop-bute. So if I said hexane, what would you give me for the formula? C7H16, because hex is 7. If I give you C3H8, what would you give me for the name? Propane, because that's what it is. In other words, these are, or this is the relationship between the name and the formula. Again, I have a Quizlet that I will upload that gives you practice with your alkanes. Yes, we can have alkanes that have 11 carbons, 12 carbons, 50 carbons. Again, the number of ways that carbon can combine with hydrogen is astronomical. It's crazy just how many ways carbon can combine with hydrogen. But I'm only going to have you memorize these 10. And the reason I'm making you memorize those 10 is because it's not uncommon for us to talk about combustion reactions of alkanes. And so I want you to know what the alkanes are. Any questions so far? Okay. The third type of covalent molecule that you're going to encounter is going to be hydrogen combined with a group 15 through 17 nonmetal. Fact is, the formula is easy to guess. Where is hydrogen on the periodic table? Hydrogen's in group 1. What charge does group 1 metal have? +1. Okay. Chlorine is in what group on the periodic table? 17. What charge does chlorine typically have as an ion? -1. +1, -1. Hydrogen to group 17. What charge does oxygen have? -2. Because it's in group 16. +1, -2. It occurs in a 1-to-2 ratio. Now, how do you name these molecules? Well, as we're going to determine, or as we're going to talk about here in a minute, it does depend upon whether they're an acid or not. The ones I'm talking about right now are not an acid. To name these compounds that are not in acid form, you name the hydrogen and you name the group 15 through 17 base with the ending I. In other words, it's done exactly like sodium fluoride. That was a group 1 and a group 17. Hydrogen fluoride. We're using the same premises here. Except for one molecule. There is one molecule that you're not going to use this process to name. And I never ever want to see this process used on this one molecule. And that is H2O. H2O is water the world over. In other words, use its common name. What we're doing here, folks, is IUPAC naming. But water is the same the world over, so use its name.
Why isn't that included in binary covalent?
Because if it's binary covalent, we would be using prefix systems. And we don't use prefixes because the hydrogen combines in a very specific ratio all the time. So you don't have to use the prefixes. Unlike the previous example where carbon and oxygen can combine in multiple ways, Hydrogen has only one way it can combine with a group 15, and that's a 1-to-3 ratio. But good question. The prefix system primarily is out there because those elements can combine in more than one ratio. Other questions? Now, I emphasize that this method is used if it's not an acid. The first thing you're going to need to know is, how do I recognize when to use this method and when to use the acid method? If I say something is an acid, I'm going to use the word aqueous with it, or the symbol aqueous with it, which is AQ. If I am indicating that something is an acid, I am going to put an AQ with it to indicate that it is dissolved in water. If there's no AQ, assume this. If there's an AQ, assume it's an acid. Which brings us to names and formulas of acid. Again, before I get into naming acids, what I want to mention is pages 1 through 4 of your packet. These give you rules to look for to help figure out how to name a compound. And it also gives you flowcharts that ask specific questions that help you to determine what category you're looking at. So, this has ionic compounds. It has the diatomic elements. It has hydrogen with group 16 and 17. I've thrown in group 15. It has the alkanes. It has the binary covalent molecules. And on the back side, it has acids. So it, again, the first 4 pages are there to help you figure out what to do, when to do it. When we start talking about acids, we're talking about inorganic acids specifically. And I'm going to read this because the type wound up blurring. First of all, an acid is going to have an acidic hydrogen attached to one or more nonmetals. To help you recognize that the formula represents an acid, I am going to use the state of matter of AQ in parentheses to say that it is dissolved in water. Now, acids can be divided into 2 types. Are they an acid of an element? If so, it's considered to be a binary acid. Or are they an acid of a polyatomic ion? In which case it's considered to be an oxyacid. I'm going to talk about the binary acid alone first. Again, a binary acid is going to be an acidic hydrogen attached to a second nonmetal. To name an acid that is binary, or what I like to say is that has the ending IDE. If you have a substance that has the ending IDE, then as an acid, you're going to give the word hydro. You're going to give the base name of the nonmetal, followed by ic acid. So again, because I know it's difficult to read in the back, if the compound, the non-acidic compound, or ends in IDE, then that becomes hydro, followed by the base, ic acid. So for example, HCl aqueous. HCl is hydrogen chloride. HCl aqueous becomes hydrochloric acid. HCN aqueous. The CN is cyanide. So this compound becomes hydrocyanic acid. H2S. This is sulfide. Because it ends in IDE, this becomes hydrosulfuric acid. For the oxyacids, which are acids of polyatomic ions, you have to know what the polyatomic ion ends in. If the polyatomic ion ends in IPE, then the acid will end in OUS acid. But if the polyatomic ion ends in ATE, then the acid will end in ic acid. Examples would be SO3 2 minus. I've already mentioned that this is sulfite. That means H2SO3 aqueous is sulfurous acid. SO4 2 minus is sulfate. Therefore, H2SO4 aqueous is sulfuric acid. Again, the key here is ic acid came from an 8 when we're talking about an oxy acid, whereas us acid came from an ite when we're talking about an oxy acid. Yes.
You told us earlier that H2S was also sulfuric acid.
No, H2S is hydrosulfuric acid. That hydro is the key to, but you're correct, it ends in sulfuric. But if you have H2S, which is a binary acid, you have the prefix hydro. Which is a good, by the way, a good catch, because no two compounds can have the same name. Now, one thing I want to point out. How many hydrogens does it have? Well, that depends upon the charge. The charge tells you how many hydrogens the oxy acid has. So the charge on the polyatomic tells you how many hydrogens the oxy acid has. So again, now that I've gone over the rules, I've even given you some examples. I will give you a few more examples. Binary acids, hydrochloric acid with the HCl, and the way I am going to tell you it's an acid is I'm going to tell you that it's aqueous. So I would have written it as HCl aqueous to help you distinguish between a binary covalent molecule and a binary acid. HBr is hydrobromic acid. Again, I will help to distinguish HBr, the binary covalent molecule, from the acid by adding the aqueous. But in all of these cases, you will notice that it starts with hydro when it is a binary acid, and it ends, whoops, with ic acid when it is a binary acid. Yes.
Are we gonna have to go from the name to the formula to the acid?
Mhm.
How do we know, like, how many of them?
How many of each? This comes, it's at the process to, so if it's a binary acid, it's the same process as if it's the covalent molecule. Meaning, if hydrogen is combined with a group 17, it's a 1-to-1 ratio. No ifs, ands, or buts. It's a 1-to-1 ratio. If hydrogen is combined with a group 16, like it is with the sulfur is in group 16, that's why it's a 2-to-1 ratio. If hydrogen were to be combined, like my example, with a group 15, it would occur in a 3-to-1 ratio. So the ratio is always the same for the binary acids. And then for the oxy acids, you just have to look at the charge on the polyatomic. So given what we've been doing, how would I name H3P? Aqueous. Is it binary or oxy acid? Binary. What do all the binary acids start with? What do all the binary acids end with? And then you simply substitute in the base of the other piece. H2SE is a binary acid because it consists of 2 elements and it's aqueous. So what do all binary acids begin with? Hydro. And they all end with ic acid. Now I just have to substitute in the base of the second element, which is selenium. So it'd be hydroselenic acid. Again, the oxy acids. It's related to the name of the oxyanion, the polyatomic ion. If the polyatomic ion ends in ATE, then the acid ends in ic acid. If the polyatomic ion ends in ITE, then the acid ends in S acid. That is true for all of them. If the polyatomic ion ends in ATE, then the acid ends in ic acid. And ite is S acid. Now, this is true, period, folks. Even for your group 17 polyatomic acids, which are a family of 4. ClO4 minus is called perchlorate. The acid is going to have, because this is a -1 charge, you're going to have 1 hydrogen, HClO4. Because this ion is an ATE, it's going to be changed to ic acid, so that's perchloric acid. ClO minus is hypochlorite. And yes, I tend to emphasize my I's, eights, and ites because they get very confusing. This is hypochlorite. Because it's a -1 charge, that's why there's a single hydrogen. When you added that hydrogen, because it ended in ITE, it becomes up acid. So this is hypochloric acid, HClO. In other words, with the oxyacids, all I'm doing is changing the ending. That's all I'm doing. Is changing the ending of the polyatomic ion once I make it an acid. Questions? Going through each type of naming by itself, it's not bad. But once you mix it up, that is when people find it challenging. That is why, again, the optional homework that says mix names to formulas and mix formulas to names, the ones that say mixed, are going to be more realistic of what you could imagine seeing on an exam than the individual homework. Questions for me? Just to let you know, the homework that's due Tuesday will have a mixture of VSEPR, valence bond, and naming. The quiz that will be the active quiz on Tuesday will strictly be naming, because you have a ton of other work on VSEPR. It takes a lot of practice. Questions? If not, that is a good place to stop for today, and we'll start all the mathematics starting on Tuesday. And you also have to develop the the idea is that you'll find all that information. So and then you can and then you're supposed to arrow it over to.
Chemistry works in molds.
So.
a meter or a-
What did you say?
Maybe it's a H2. On the mold, what happens on that? For some reason, it's not. Well, there's that.
There's sodium chloride in the compound, but once you put sodium chloride in water, it's just chloride. That's the only thing that happens. We don't use it. We don't need more in it. So, today. That's the word. Yes, okay. So I won't be here until. Okay. So. I will go back. Great, bring you back on. I'll shoot it. I will be coming. Sitting out here being. Okay. So I will try to see sometime next week. Maybe that'll be. That would be good. Yeah. Because I know that'll be hard. I will be seeing you next week. Okay, sounds good.